So in this video, we're going to explain why it is that 21st century skills like creativity, communication, collaboration, critical thinking, all those things which are supposed to make you a better learner and a better person actually don't really work, and they lock you out of doing the actual things you need to do when studying and when learning. So this is going to be a critique of so many of the problem solving, critical thinking, creativity, generic types of programs which are supposed to improve you. Why doesn't it work, and why should you not be doing it as a teacher or as a lecturer? Now, the key paper we're going to be working on is a paper by Sweller. Now, Sweller is one of the key guys involved in cognitive load theory, and he's written this paper called Cognitive Load During Problem Solving, Effects on Learning. Now, it's an old paper. It was written in 1988 in cognitive science, but it is very clear in terms of its outcomes, which should have actually percolated through the whole education system by now. And Sweller says there is no clear evidence that conventional problem solving is an efficient learning device, and there's considerable evidence that it is not. So don't think that just because you're using problem solving techniques in your lectures and your classes that somehow you are doing something wonderful for your students or kids. Chances are, if you haven't given them the structured knowledge they need to answer the problem, you're doing them a disservice. Okay, so now they're going to try and justify it, and they're going to talk to why this article is so important. And bear in mind, this is coming from How Learning Happens, a brilliant book by Kirshner. So now they're going to start off by talking about cognitive load theory, and you'll see I've done a whole series on it. And Dylan Williams says it's the single most important thing for teachers to know. And I agree with that. That's why I focused it on as the main thing we need to understand in order to improve technical and vocational education. And it's based on a very simple principle in cognitive science, and that is the limited ability of working memory to code information. So in your brain, currently working is working memory, which can only take a certain number of things in. And if you overload it with all sorts of crap, all sorts of things the kid or student can't do, well, they're not actually going to be able to focus and learn. So what do you need to do? Well, you need to build up schemata of knowledge that allow them to work on problems without exceeding their cognitive bandwidth. The more they understand about the issues that they're dealing with, the more they're able to actually focus on the problem. Then, and only then, they can work independently. It's not that you don't want them to problem solve. It's not that you don't want them to work independently. That's a great sought after goal. But don't do it right at the beginning. Okay, so now we do know that this is this problem-solving idea is the hottest topic in education, and it is actually. It's continuously there, and it forms the basis. And here I'm just going to get a bit technical for the students out there. It forms the basis for constructivist approaches to teaching. Now, constructivist approaches, you can hear it in the name there, constructivist, right? Construct. And what they're going to do is they're actually going to define it for you. Theory that we construct knowledge from our experiences. So you build it up. You get it from the way that you experience things, and the more things that you can create in a way where the student tries to experience what's actually going on, the better it is. Now, the issue with that is if you're trying to build up your knowledge piece by piece through experience, and you don't have a broader, bigger schemata which to place it in, that knowledge building is not going to make much sense. It's not that you don't want to construct. It's that you want to construct into something which is bigger than that, that gives it order, coherence, and sense making. Right? So all these things like problem-based learning, inquiry-based learning where you ask questions and try to work out what's going on. Discovery learning, oh wow, how can this be bad? How can it be bad to have something like inquiry? That's good. And discovery, oh, that's fantastic. Experiential, oh, it's got to be good. It's got to be good. It's only good if you're discovering in a situation where you already know some of the knowledge that's in that zone. Otherwise, you're walking blind. You don't want to discover as a blind man. You want to discover as someone who can actually work through the stuff in a way where it makes sense. So, given that that's the case, we are kind of critiquing this kind of idea that the most important thing at the moment is the acquisition of generic, in other words, all-purpose, things that you can work in any situation, domain independent, in other words, it doesn't depend on specific knowledge and specific ways of doing things. It can work for anything and everything. It's domain independent. That's the best way to learn how to solve problems, right? You work out to solve them by actually trying to solve them. And it doesn't matter what the area is, it's the fact that you've got the generic skill, the all-purpose skill to solve the problem. Well, what's the problem with that idea? Okay. Well, let's say you're confronted with a problem to solve. If you're, and I'm going to go to blue here, if you're well versed in the subject area, that is to say you have a great deal of knowledge relevant to solving, and just by the way, I'm going to go to the next page, but this is the article it's taken from, Sweller, 1988, Cognitive Load During Problem Solving, Effects on Learning, and it's in Cognitive Science. And I will do another video on it. Right, so now if you've understand the area and you've solved similar problems, well then what you're going to do is you're going to know what the necessary steps are to define, solve, and evaluate your solution. You can choose between different problem-solving strategies and you can go to what you've used before. And you do that after determining its similarity with the problem at hand and whether the strategy which you're thinking of using is relevant. Now that's how experts work, right? Now what are they doing there? They're making use of the knowledge and strategies that have been stored in long-term memory. Now that is domain-specific knowledge, right? That's specific knowledge about that specific area. It's also domain-specific procedural knowledge. In other words, procedural, knowing the steps you have to take to get to the solution. So procedural is steps, right? On the other hand, if you're not knowledgeable in the area, if all you've got is generic skills, well, then you're in trouble. I promise you, you're in trouble. You're going to land up doing what's called means end analysis. And yeah, you work backwards. You compare your current state, where you are at the moment, with the goal state, where you need to be the solution, and you look for moves that you can possibly carry out. So what happens is, you over here, the solution is over there. Here's the problem. There's the problem which they've given you. And what you do is you go, I'm over here. That's over there. What do I do? Well, maybe I try to do that. No, maybe this works. Maybe I've got to try that. And you try and slowly but surely get yourself towards understanding this. But you're doing that to and fro because you don't have a large base of knowledge and procedures in which to identify this problem and then work towards solving it. Now, the key thing that they're going to say about this is when you do that, it requires much mental effort. And remember, we're talking cognitive load theory here. What are you doing? You're searching for and finding problem-relevant information. It's hard to do. It's hard to find this problem-relevant stuff if you don't know much about the area. And what's happening is you're landing up in high mental effort, trial and error, which is neither effective nor efficient. And guess what happens? You get frustrated at how long it's taking. You get all these dead-end encounters. And in other words, the process is not very enjoyable. So the very idea of you as a teacher or lecturer trying to make things more stimulating and interesting by giving kids problem-solving things to do doesn't work if they don't have the base on which to do it. Right. So there we have the story itself. And that's the idea. And let's go into the article itself so we can actually see some of the stuff that he says. And basically what John Sweller is going to do is he's going to work on extensive research on the expert-novice distinction. And I've done a previous video on this. And how do they differ? Well, They differ in terms of their memory of the problem state configurations. Problem state configurations. In other words, what is this thing that's over here, and what are the possible ways we can do and solve this situation? What's the different setups in which this problem sits in? What are the different things I can come to get to answer the issue? And that's domain specific. And then they've also got problem solving strategies. And the problem solving strategies are very different for novices and experts. Remember, the novice is going to work with a means end. They're going to work backwards and forwards trying to get at the solution. Whereas the expert, in terms of where he is over here, is going to have all sorts of possible solutions, which they're going to go, it's this one which I've got to use to solve this. And this one has these steps, and therefore I'm going to try these steps and solve the problem. And you as a teacher want to make sure that you're building this state, the schemata in the learners, so that they can actually solve the problem in the long run. Okay, and the example that they've got, this famous example that they're working with, are chess players. And it's a fantastic study actually by De Groot. He wrote a wonderful doctorate. And what he showed was that grandmasters who we think are gods, they're superior and they're fantastic. Actually, no. They don't have a better working memory than us mere mortals. In other words, their working memory isn't super powerful or supercharged. It's not that they are more creative or better at solving problems. None of these things. If you test them on normal situations, they're not more creative. They're not better at problem solving. They haven't got a superior working memory. What's actually the difference between these buggers and us is that they can remember more meaningful chess positions. They've got a bigger schemata in their heads. They've got a larger base to work from. And we have to work on that with our students. And in terms of problem solving strategies, the strategies used by experts and novice problem solvers also differ. As I've told you, novices tend to work with that means end analysis, while experts, in contrast, begin by choosing a strategy they're familiar with, usually from solving an analogous problem, in other words, a problem which is very similar. And once they've got that strategy, they then work forwards to solve the problem. So you can hear what's happening over here. Here's the issue which they've got to solve, right? So what the expert does, she is. And what happens is, in her brain, she's got all sorts of possibilities and schemata for solving the problem. She identifies which two could possibly work. She checks it out over there, and then she uses these techniques to solve the problem. She's working forwards. But she's only working forwards from a baseline of already having a lot of understanding of what the issues are. Okay, and they're going to say that. They're going to do moves which, that's the wrong, let me just get rid of that. They're going to do moves which are appropriate. They have cognitive schemata in their long-term memory, which allow this. And interestingly enough, and you'll have seen this in the previous video I did, the features that they use to categorize the problems are very different. Now, what happens with the expert is they look for deep structures. They look for the deep principles that inform things. And you only get that from actually being deeply immersed in the subject that you're working on. And that's your job as a teacher, to introduce them to that stuff. Whereas the novice, I'll do it in green, they work according to surface structures. And you can see the person, there's Chi, Glazer, and Reese. And you'll see a video that I've used in this. Right? So now, what's the issue? If you use inquiry-based instruction, it requires the learners to search a problem space for problem-relevant information. Now, that problem-based searching makes heavy demands on working memory. And that working memory load in the search doesn't contribute to the accumulation, does not contribute to the accumulation of knowledge in long-term memory. Why? Because whilst working memory is being used to search for problem solutions, it's not available and cannot be used to learn. So the very thing you're trying to do to help your learners to learn, give them a problem-based issue or an inquiry-based situation where they're going to explore. That's precisely what is not enabling them to learn, because their working memory is wrapped up in that kind of stuff and not learning the stuff that they need in the first place in order to be solving the problem. And there we have why the title of the second chapter in the book, How Learning Happens, is Take a Load Off Me. Do your job as a teacher. Get the students to understand what's going on and get them to have the base from which they can solve problems, and then go for it. Get them to solve problems, because it's the most exciting thing you can do as a teacher, but only when the kid already understands what's going on.